Welcome to a lesson on Webster's method of apportionment. Daniel Webster proposed a method similar to Jefferson's method in 1832. It was adopted by U.S. Congress in 1842, but was replaced by Hamilton's method in 1852. It was then adopted again in 1901. The difference is that Webster rounds the quotas to the nearest whole number rather than dropping the decimal parts. If that doesn't produce the desired results at the beginning, he says, like Jefferson, to adjust the divisor until it does. It's important to note that in Jefferson's case, at least the first adjustment will always be to make the divisor smaller. This is not always the case with Webster's method. To apply Webster's method, we first determine how many people each representative should represent. We do this by dividing the total population of all the states by the total number of representatives. This answer is called the standard divisor. 2. We divide each state's population by the divisor to determine how many representatives it should have. We record this answer to several decimal places. This answer is called the quota. Step 3 is what's different about Webster's method. We round all the quotas to the nearest whole number. Then we add these values, which can be called the initial allocation or initial apportionment. Step 4, if the total from step 3 is less than the total number of representatives, we reduce the divisor and recalculate the quota and allocation. If the total from step 3 is larger than the total number of representatives, then we increase the divisor and recalculate the quota and allocation. We continue doing this until the total in step 3 is equal to the total number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. Let's take a look at our first example. The legislature in a state has 44 seats. We want to apportion these seats to the 5 counties below using Webster's method. We want to begin by finding the standard divisor, so we find the sum of all the populations, which is 1,582,000. We divide this by the number of seats, which is 44, giving us a standard divisor of 35,954.5455. So to find the quotas, we take each population and divide by the standard divisor, which I've already done here to save some time, but let's go ahead and check at least one of them. To find the quota for Adams, we would take 365,000 and divide by 35,954.5455, giving us our quota of approximately 10.152. We would do the same for the 4 remaining counties. And now for Webster's method, for the initial allocation, we'll round the quota to the nearest whole number. So if we have a 5 or more in the 10th place value, we'll round up. 4 or less, we round down. So for the first quota, we would round down to 10. For the second quota, we would round up to 14, again because of the 6. Here we would round down to 7. Here we round down to 5. Here we round up to 8. And now we find this sum and compare it to 44. If it is 44, we're done. If it's not, we have to adjust the divisor. Here we lucked out because this total is 44, the number of seats that we have to apportion, so we are done. Our initial allocation is our final apportionment. Many times we don't find the final apportionment the first time, so let's take a look at a second example. The number of salespeople assigned to work during a shift is apportioned based upon the average number of customers during that shift. We want to apportion 15 salespeople using Webster's method given the information below. Notice how we have 4 shifts, so the first step is to find the standard divisor. So we sum all of the customers over these shifts, which gives us 1,340. We divide this by the number of salespeople, which is 15, giving us a standard divisor of approximately 89.3333. Now we find each shift's quota by dividing the number of customers by the standard divisor. And again, let's go ahead and check at least one of these. For the morning shift, we'd have 145 divided by 89.3333, giving us a quota of approximately 1.623. We would do the same for the remaining shifts. So here are the quotas, And now we're going to round these to the nearest whole number. So again, if we have a 5 or more in the tenths place value, we round up. 4 or less, we round down. So the first quota rounds up to 2, the second quota rounds down to 3, this rounds up to 5, and this rounds up to 6. Notice how the total here is 16, but we can only apportion 15 salespeople. And therefore we have to adjust the divisor, and because this is too many salespeople, we'll have to increase the divisor. Let's begin by changing the divisor to 90 and see what that does for us. So now we'll begin by recalculating our quotas by dividing the number of customers over each shift by 90. So again, let's go ahead and check at least one of these quotas. For the morning shift, we would have 145 divided by 90, giving us our quota of approximately 1.611. Notice for the midday shift, 270 divided by 90 would be exactly 3. Let's go ahead and round these to the nearest whole number. So this would round to 2, this stays at 3, this would round to 5, this would round to 6. But notice how still this sum is 16, it's too high. So again, we have to adjust the divisor, so we'll increase it more. Let's go ahead and increase this to, let's say, 92. Recalculate the quotas by dividing these values here by 92, which are already given here. Let's go ahead and round to the nearest whole number. This first quota we round up to 2, here we round up to 3, here we round up to 5, here we round down to 5. Notice finally we do have the right amount of salespeople. We have 15 here with 15 salespeople. This would be our final apportionment. So this is how Webster's method works. A couple more things we should mention. Like Jefferson's method, Webster's method carries a bias in favor of states with large populations, but rounding the quotas to the nearest whole number does greatly reduce this bias. Also, like Jefferson's method, Webster's method does not always follow the quota rule, but it follows the quota rule much more often than Jefferson's method does. In 1980, two mathematicians, Peyton Young and Mike Belinsky, proved what we now call the Belinsky-Young impossibility theorem. The Belinsky-Young impossibility theorem shows that any apportionment method which always follows the quota rule will be subject to the possibility of paradoxes like the Alabama, new states, or population paradoxes that we've already discussed. In other words, we can choose a method that avoids these paradoxes, but only if we are willing to give up the guarantee of the following quota rule. And we've already covered the quota rule, but here it is again. The quota rule says that the final number of representatives a state gets should be within one of that state's quota. Since we're dealing with whole numbers for our final answers, that means that each state should either go up to the next whole number above its quota or go down to the next whole number below its quota. That's going to do it for this lesson. I hope you found this helpful.